I started to record. Tell me, you see the board, yes? The whiteboard. My writing.
Yes.
Okay. So now, the title of our lecture, at least the first part, is to study functions of one single variable by using derivatives. So we shall have a function which is defined on some set D included in the set of real numbers. Usually it is the entire set of real numbers or an interval or a union of intervals. Yes, and we want to answer to questions like this: monotony and local extrema, and other related questions. For example, let's have a pic. Imagine that we have a function whose graph is the following. Something like this. What we can see in this generic function. There are intervals on which the function is increasing. It takes, if you have here a point x1, another point x2, the value at x1, it's smaller than the value at x2, so x1, it's less or equal than x2, it implies f of x1 less or equal than f of x2. We call that the function is increasing. Increasing, yes. There are other intervals. For example, here, if we take 2 points x1 and x2 here, we observe that x1 is less or equal than x2, and the function at x1 is greater than the function at x2. We call such a function decreasing. Yes, and so on. In general, a function, it is increasing on some intervals and decreasing on other intervals. For instance, here again at this point, again, the behavior of the function is changing. It becomes increasing again. Okay, so this is the problem of the monotony, to discover the intervals on which the function is increasing or decreasing. Related to this question, we have the problem of local extrema. Local extrema are A is a, for instance, local maximum. If there is an interval around that point, for instance, this one, A, at which, on which the function is less or equal than the value at A. As you can see here, for example, at the point A, the value f of A of the function is the highest on the graph. That means the value of f at A is the greatest around this point. It is not necessarily the greatest value of the function because, for example, here at this point, the function takes a greater value, but that is not a local. So local minimum, that means the following. F of x, local maximum, is less or equal than f on, for x, on some interval, a minus r, a plus r. So there is an interval around this point on which the value at a is the greatest. This interval could be smaller or greater, doesn't matter. A is called a local minimum if f of x is greater or equal than f of a for every x on some interval around the point A. Yes. On this picture, this one A here, this A, it's a local maximum, while this one here, it's a local minimum. As we can see, the extrema, this is called an extremum point. So these are local extrema. Local extrema could be local maxima or local minima. Okay, so as we can see on this picture, the two questions, monotony and local extrema, are related because, for example, a local maximum is like the function at the left of a local maximum is increasing, and at the right is decreasing. For a local minimum, the function at the left, it is decreasing, and then it is increasing. Okay, so for both problems, we have the same tool, namely the derivative. I will try to sketch the idea of the derivative. So if A is if we have a function f defined somewhere on D with values, and if A is a point in D, the tangent line of at the graph of f at the point A, this is its name, it's long, but it's the tangent line at A. It's a straight line. I shall try again a picture. So imagine the graph of f is like this. So if we take here a point A, and the value of f at A is f of A, through this point there are infinitely many straight lines passing through, like this, like this, like that, and so on. So the tangent line, it's from the geometrical point of view that straight line which passed through this point, and it is the most similar in this region with the graph of the function. So if you want another, to put the problem like this, if you want to replace this picture, the graph of the function around this point, so close to this point, with a segment, what segment would you choose? This is the question. For example, surely this is not good. Yes. Well, the answer is given by the so-called tangent line. On our picture, it is close to this one, but I shall make another picture again. And then we shall write its equation, because being a straight line, it has an equation. So the problem is solved in the following way. This is the graph. Take the point A and f of A. And the idea of the tangent line, it's, let's say, something like this. Okay, and the problem of the tangent of this tangent line, it passed through this point, so we know that it passed through this point. But what we still need to know its equation is the slope. The slope. Do you know what is the slope of a line, of a straight line?
No.
You don't. You know?
Can you remind, please?
Okay. So we make a parenthesis now. Let's consider a straight line, something like this. Yes. Then the slope of this straight line is defined as follows. Every such straight line has an angle with the horizontal axis OX. Yes, this is the horizontal axis OX to the right. So the angle between OX and this straight line is this one. It's an angle. Yes. Well, the trigonometric tangent, that means tangent, this angle has an, let's call it alpha. Tangent of alpha, which is sine of alpha over cosine of alpha, is called the slope of our straight line. Yes. For example, but don't worry, it's not too much trigonometry here. You will see. For example, if our straight line, it is this one, making here an angle of pi over 2 radians, or in degrees, that means 45 degrees. Tell me, who is the slope of this tangent line? Of this, sorry, not of this straight line. Can we compute the slope of this straight line? It's tangent of 45 degrees, which means, do you know the value of the tangent function at this point, at this angle?
It's 1.
It's 1, very well. So this straight line has the slope 1. Yes. For example, if the angle is, let's say, this one, pi over 3, so the larger angle is pi over 3, then, or 60 degrees, if you want in degrees, tangent of 60 degrees equals, do you know the value?
The square root of 3.
Square root of 3, very well. So, in that case, this straight line, this one, has the slope square root of 3. Yes? For example, if our straight line is the horizontal axis, this one, or any other straight line which is parallel with it, the angle is 0. Yes? The angle between the axis OX and the parallel with it, it's 0. Tangent of 0 is 0. So the horizontal straight lines have the slope 0. Yes. So now we have I think we begin to have a sort of image about slopes of straight line. So horizontal straight line has the slope 0. Now, when the angle is increasing, the slope is increasing. For example, when we arrive here, when the angle is pi over 4 radians, the slope is already 1, as you remember. When the angle here is pi over 3, the slope was square root of 3, and so on. When the angle is increasing, the slope is increasing. When our straight line becomes a vertical line, well, vertical lines here means the angle is pi over 2. When the angle is pi over 2, the tangent doesn't exist, because tangent of pi over 2, it's sine of pi over 2, which is 1, over cosine, which is 0. So this one is meaningless. We make a convention. We say that vertical lines has the slope infinite. Infinite or minus infinite, we do not make any distinction between these two values, which are not numbers. So horizontal straight lines has the slope 0, up to, and now the slope is increasing, up to the vertical lines where the slope is infinite. It could be infinite or minus infinite. We don't make a distinction between these two values, arbitrary values. Okay, and now this is the position. Until here, the position of our straight line was like this, is increasing. So when you go to the right, as you see, you climb. The position is higher and higher when you go to the right. This was the case. So this kind of straight lines, yes, have the slope positive from 0 to infinite. These are the extrema values of the slope. But anyway, these straight lines which are climbing, when you go to the right, have a positive slope. Now, when the straight line is like this, the slope is negative, because tangent of an angle which is greater than pi over 2, it's negative. So here it's the region of straight lines with negative slopes. For example, when here this angle is 3 times pi over 2, in degrees this is 135 degrees, so 3 times this one. 45 degrees, and another 45 degrees here. The tangent of 3 pi over 4, it's minus 1. So this straight line has the slope minus 1. So it starts from minus infinity here. It goes down, and the slope is going in absolute value smaller and smaller, and so on up to 0. So the image, a good image for how the slope is changing. So horizontal straight lines have the slope 0. Then as the angle here is increasing, the slope is increasing. Here already we have the slope 1, and here we have infinite. Now going now to the left, that means taking straight lines which are decreasing. For example, here the slope is minus 1 because it started with minus infinity, minus 1 million, minus 1,000, minus 1. And it goes back to 0. This is the image of the slopes associated to straight lines. Okay. So the slope gives us the direction of a straight line. If I tell you, for instance, I am thinking to a straight line with a slope, usually the notation for the slope is the letter M, whose slope is, for example, minus 2. Do you have an image of, an approximative image of how this straight line looks like? Yes, because it has a negative slope, so it must going down like this. And it's minus 2, so it is somewhere between minus 1 and minus infinity. It's something like that. So a straight line whose slope is minus 2, it's somewhere over here, approximately, of course. A straight line which has the slope, for example, 1 over 3, so it is between 0 and 3. It must be somehow like this. It is increasing because the slope is positive, but it is less. It is much closer to the horizontal than to the vertical because it is 1 over 3. Okay, this is the image about the slopes. Anyway, positive slope means a straight line which is increasing. A negative slope, it's a straight line which is decreasing. Okay, and now we have an equation which gives us, first of all, how to compute the slope. So how to compute the slope? The slope can be computed in a very simple way if we have the equation of the straight line. As you know, the equation of a straight line looks like this, where A, B, C are numbers. So to find the slope, you have to explicit y. Take off y from here, it will be minus A over B x minus C over B. So the slope is the coefficient of x. Of course, this can be done if B is not 0. So you, from the general equation of the straight line, explicit y, and the coefficient of x, it can be proved in a very simple way. The coefficient of x is the slope. For example, if we have the equation 2x plus 5y minus 3 equals 0, to find the slope of this straight line, we take off y. So we explicit y in terms of x. That means this. So y will be minus 2 over 5x plus 3 over 5. So the slope of this straight line is minus 2 over 5. Okay, if it is clear until now. So we have a very simple way to find the slope of a straight line as long as we know its equation. This is an equation of a straight line. Is it clear?
Yes, yes. So
if
the
you have
slope
something,
is the value.
if you have something to ask, please ask.
The slope is the value near the x, right?
Please.
the slope is a value near x.
The slope is I don't understand one word there. Is the coefficient of x. Without
Yes.
x. It's just the coefficient, it's a number. The slope, it's a number, is the coefficient of x when you explicit y. Yes?
Yes.
For example, another, if we take x plus 2y plus 3 equals 0, how we can compute the slope here? We explicit y. 2y equals minus x minus 3. So y equals minus 1 over 2 minus 3 over 2. Sorry, here it's x. So the slope is the coefficient of x. This is it. The slope here is minus 1 over 2. Yes?
Yes.
Okay. And now another issue. From geometry, we know that we can write the equation of a straight line in two situations. When we know 2 points, we know the point A of coordinates x, A, y, A, and B of x, B, y, B. So we know the coordinates of 2 points in the plane. Here it's A, here it's B. Suppose, yes, the coordinates of these 2 points are given. Yes, and then the straight line which passes through these 2 points, this one, the so-called straight line AB, it's known because if we know 2 points on a straight line, we know the straight line. So it's normal to ask, what's the equation? We must know it's very simple to prove that the equation of the straight line which passes through these 2 points is the following. So the equation AB, the equation of the straight line AB is given by x minus xa over xb minus xa equals y minus ya over yb minus ya. For example, let's write the equation of the following straight line. A of coordinates 1 minus 3 and B of coordinates minus 2, 4. Who is the equation of the straight line which passes through these 2 points? AB. We have this formula. Okay, let's use it. So x minus xa. Xa it is this one. Yes, this is xa. This is ya. This is xb. This is yb. So x minus 1 over xb. Xb is minus 2 minus 1 equals y minus ya, which is minus 3. And below we have yb, which is 4, minus 3. And now we make the computations and we get the equation of the straight line AB, the straight line which passed through these 2 points, A and B. So it's x minus 1 over minus 3 equals y plus 3 over 7. We eliminate the denominator, so 7x minus 7 equals minus 3y minus 9, which means 7x plus 3y plus 2 equals 0. This is the equation of the straight line which pass through the points of coordinates 1, minus 3, and B of coordinates minus 2, 4. I want to know if this is clear.
Yes, it is.
Okay, and now a question for you. Please compute the slope of this straight line. As I said, we usually denote the slope by the letter m of some straight line. The slope of the straight line AB, for example, call it m and x AB equals what? Please compute it and tell me the value.
7/3.
Not 7/3. You are close, but not exactly.
No, minus.
Minus 7/3. So this is the slope, yes? Okay. And now, please do the following computation. For the same straight line, we are talking about the points A, B given here. For these 2 points, please compute the following expression. Compute this expression where the coordinate, these 4 coordinates are known. They are here written. And I wait for you to tell me the answer.
Minus 7/3.
Minus 7/3, very well. So as you can see, this is exactly the slope. Yes, you understand what I'm trying to say. So the conclusion is the following. If we have 2 points, yes, we know to do 2 things. First of all, we know to find the equation of the straight line which passed through those 2 points. Yes, this is given by this formula. But also we can compute directly without using the equation. We can compute the slope. So the slope of the straight line AB is given by this formula. Yes. So which allows one to compute the slope of a straight line if we know 2 points on that straight line, but without computing first the equation of the straight line. Yes, you understand what I'm trying to say? Yes,
Yes.
we get directly the slope. Okay, very well. And now the last thing about straight lines, because this is a analytical geometry, a lesson in analytical geometry about straight lines. It's the second case when we can find the equation of a straight line is when, so the first case was when we know 2 points, this case, this one. And now imagine a straight line and imagine that we know a point. That's the point P of coordinates P, XP, YP. And we know the slope. The slope, which is a number, M, is given. If we know the slope, that means we know the direction of our straight line. So in that case, the straight line can be found because it is only one straight line which passed through a given point and has a given slope. The equation of the straight line, please write in words, the equation of the straight line which pass through the point P of coordinates XP, YP, and has the slope M, a given number, is, this equation is Y minus YP equals M times X minus XP. Again, the formula can be proved in a very, very simple way. It's very, very simple. But it's important. We must know it. So now a short revision of what we learned about straight lines. Yes, I will make a resume. about straight lines. So the general equation of a straight line is an expression or is an equation in x and y of the first degree. Okay. What we know, we learn about the slope, which is a number which can be computed as we observed. We already know. We explicit y from here. What we still know, we know that if we have 2 points, A and B, we know how to write the equation of the slope of the straight line AB, and also we know how to compute the slope of this straight line. And finally, if we know 1 point, the coordinates of 1 point, and we know the slope, again, we know the equation of the straight line, yes, which is given here. This is the resume of the theory of the equation of a straight line, and we must know it. Okay, if there is something unclear here, or if you feel that maybe another to do another example, or if the things are clear, we can go further. And actually, we shall go back. Yes, please.
I think we can go further.
Okay, so now we shall go back to the study of functions, because this was our main subject. This is a parenthesis which will help us in the study of functions. And now let's go back to our problem. Our problem was the following. We have a function, a point in the domain of definition. The point on the graph of the function has the coordinates a and f of a, and we were interested to find the slope of the tangent. So our graph, let's say, looks something like that. Okay, so let's take a point here of coordinates a and f of a, and we would like to know the equation of the so-called tangent line at the graph of the function. On this picture, it looks something like this. Now, to know the equation of this straight line, this is the tangent line. Okay, what we need to know, we know a point already, and now we need another point. And if we know another point, we can write the equation, because remember, if we know 2 points on a straight line, we know the equation. We have a formula. Or equivalently, we need a slope. If we know the slope, again, we can write the equation of the tangent line. Now, another point we cannot find on this straight line. So what we are looking for is the slope. So the problem is to find the slope of the tangent line. And the method is like this. Let's take another point on the graph of the function of coordinates x and f of x. This is the point of coordinates x and f of x. And now let's consider the following 2 points: a, f of a, and x, f of x. Okay, what we can observe on this picture, if x is closer and closer to a, then the position of this straight line, you see, if I move the point here, the position will be like this. So if x is closer and closer to a, then this straight line, which passed through this point and through this point, will be closer and closer to the position of the straight line. So we can imagine that when x tends to a, their slopes will be equal. Now, who is the slope of the straight line which pass through these 2 points? We know we have a formula that is f of x minus f of a over x minus a. This is the slope of the straight line passing through the points of coordinates x, f of x, and a, f of a. Is it clear or not?
It is.
So I'm talking about that formula, yb minus ya over xb minus xa. Yes, here this is the point a, or b, let's say call it b, and this is the point a in our previous notations. And the slope was the subtraction of the y coordinates, and below we have the subtraction of the x coordinates. This is the slope. And now, to obtain the slope of the tangent line, we need to take the limit where x tends to a of f of x minus f of a over x minus a. Because as we observe, when x is closer and closer to a, this straight line will be closer and closer to the tangent line. Well, so in this way we arrive at the definition of the derivative. We suppose that this limit exists and it's a number, and we denote it by f prime of a, and it is called the derivative of f at a. Yes, and it's a number. And its definition, it is this limit. It's not an elementary definition, it's a limit, but anyway, it's not very complicated. Okay. This is the definition of the derivative of a function at some point a, of course, under the hypothesis that this limit exists and it's a number. It's not infinite, or it doesn't exist. Okay. And now what's the use of this number? This is the slope. On the other hand, it is the slope of the tangent line. So in this moment, we can write the equation of the tangent line at the graph of f at x equals a. According to our previous equation, we know the point a, f of a, and we know the slope f prime of a. So the equation will be y minus f of a equals the slope f prime of a times x minus a. This is the famous equation of the tangent line at the graph of a function. Here I'm talking about the following general formula: y minus yp equals m times x minus xp. Here the point p has the coordinate a, f of a, and the slope m is the derivative of f at the point a. Okay, so now we know the equation, and we know the slope of this equation, of this straight line, is the derivative. This is the most important fact. Okay, so consequently, let's imagine the following situation. We have the graph of the function like this. Let's take a point here. You see here, in this region, the function is increasing. The tangent line looks something like that. Okay? How is the tangent line in a region when the function is increasing? It is also increasing. Yes? So how is the slope of the tangent line in a region where the function f is increasing? How is the slope of this straight line? Positive or negative?
Positive.
Positive. So we discover the following. If the function is increasing, its derivative must be positive. For instance, here, the tangent line looks like this. Here, the function is decreasing. The tangent line is going down. Its slope will be negative. So we discover the following. In a region when the function is decreasing, the derivative is negative. So the function is decreasing, then the derivative is positive. The function is decreasing, then the derivative is negative. Of course, everything under the hypothesis that the derivative exists at every point. If there are functions which do not have derivatives at some points, but we are not interested for the moment in that kind of functions, yes? Okay, and now what about extrema? Well, the function is changing the monotony at some point here, which is a maximum, of course, yes? Up before a maximum point at the left, the function is increasing, and then it is decreasing. So here at this point, the derivative must change the sign until here it is positive, and then it becomes negative. So at the point A, what value the derivative must take? Until here it's positive, then it is negative. So here, the point where it changed the sign, the derivative must be how a function can change the sign from positive values to negative values. It must take the value, what value at the point where it changed the sign. Think to usual functions. It cannot change the sign if it is not zero. For example, do you know the sign of the quadratic function? Let's take a quadratic function, x squared minus y. Do you know the sign of this function? What sign it takes? Do you know what the sign means? Positive or negative? Yes. Let's make the sign of this elementary function, for example. Do you know to make the table of sign of this function?
Yes.
Okay, let's do it. In our first lesson about at the Rose class here, we have a revision of usual simple functions, and we started with linear functions, quadratic functions, and so on. The sign of this function looks like this. Yes, on the interval minus infinity minus 1, it is positive, then it is negative, and then it is positive again. And what can we observe? That when the function is changing the sign from positive to negative, it must take the what value?
The zero.
Zero. It cannot change from positive to negative, or again from negative to positive, if it doesn't take the value zero. Think a little bit, and it's normal. Yes. So coming back to our, so what's the value of the derivative at this maximum point? At the left, the derivative must be positive. At the right, the derivative must be negative. So at this point, it must be zero. Yes, the tangent line here is horizontal. Because remember, if a straight line has the slope 0, it is horizontal. So at an extremum, at a local extremum, the tangent line is horizontal. Yes, where it is. So we also discover the following: if A is a local extremum, then the derivative of A must be 0. Okay, so this is the theory which will help us to answer to our questions. Study the monotony of a function and find the local extrema. Okay, now we have already 1 hour. We can take a break now and continue. What time is your limit time? How much can you stay? Can you stay another hour?
Yes.
Okay, so now we take a break, and after 10 minutes we shall come back with our main goal, which means compute study study the function, the monotony and yes.
Okay.